Hello, Words. Are you ready to share?
Yes, yes.
Uh, I will just a simple introduction, then you can share.
Okay.
Okay. Hi everyone. Today I'm pleasure to have Wolfgang Wells at Open Course to share how to build with Boundless. Uh, Open course, just like the name, is an online open course. We focus on blockchain technology. Uh, Open course organized by Upchain, 登链 in Chinese, Libase and open build community. Welcome, World. You can
Okay.
start your show.
Yeah, thank you. So first, my name is Wolfgang Welz. I am not Jacob, who was originally supposed to hold this workshop, but we had to do some last minute changes. And so now I'm here to do today with you. I'm actually an engineer at RiskZero and a core developer at the Boundless protocol. So I hope I can give you a pretty good introduction on how to use our Boundless protocol. So let's first start by understanding our motivation, why we put our efforts towards the Boundless protocol. So we at RiskZero, we were actually the first to build the general purpose ZKVM. And this enables a lot of possibilities, but it's still by itself does not address the fundamental challenge that we have with current smart contract blockchains, namely their computational limits. So why is that the case? That is due to the current consensus mechanism in blockchains like Ethereum. And that is, if I do a complicated smart contract computation, I submit it to the network. And then every node in the network essentially has to rerun the same execution, the same computation I performed to verify that this is correct. And so that means not only myself, the one that sends in the transaction, has to do the work, but everyone. And the worst case is obviously if I send in like an infinite loop, and then now everyone has to tries to run this infinite loop, and the whole network stops. So this doesn't work. And what you do as a countermeasure is you introduce you make the computation limited to what you can do in one block, the gas limit. And this also, like this limit itself, has also some other drawbacks. Namely, if you rerun everything, you're always limited to the slowest node in the network. If you, let's say, you want to say my blockchain is supposed to run on a Raspberry Pi, then you cannot go faster than the slowest node in the network the Raspberry Pi can go, even though you might have a super fast computer. And that in general leads to higher cost and underutilized computational capacity. And ZK by itself offers a paradigm change and offers a solution to that. And why is that? So with the ZK model, no longer you have to do re-execution. Just the one node that basically sends in the transaction, they have to do the work. And in addition to the execution, they also create a proof that this execution is correct. And now every node in the network, they don't have to rerun the execution. They just check that this proof is correct. And the beauty or the bit of magical thing about ZK is that the verification of such an execution is does not depend on the on the computational complexity you have performed. So in general, to simplify it a bit, it doesn't matter whether you compute the 1 billionth digit of pi or just trivially the 10th digit of pi. The proof and the verification will be the same. So at some point, it'll pay off to use this. And that is exactly where we used to have a limitation. Of course, it doesn't make sense if verifying a ZK proof takes longer than your execution. But fortunately, we have seen an enormous improvement in the performance of ZK virtual machines in the last year. And now it has become feasible to run arbitrary compute, create a proof, and then just verify it. Because in general, this is more efficient than rerunning everything. And now suddenly, I don't have this dilemma that the consensus needs to rerun everything and I'm bound to the slowest node. Now I can basically do as complex work as I want, as long as I'm personally willing to wait for the execution. Then I create the proof, and then every node in the network can verify it, no matter how complex my execution is. And this completely removes the need for gas and other limitation, and is of course a huge paradigm shift in blockchains. So the question remains, why aren't we seeing that much adoption? And the issue is that it is more than just running a virtual machine. There are many, many moving parts that come into play here. So for example, who's the prover? Who's going to prove what? How can you facilitate payment of the provers? How can you verify such a proof on chain? How can you basically link the blockchain Solidity world with those proofs? And Boundless actually aims to address exactly that. So Boundless is our universal ZK protocol. So we're not just building NL1, NL2. We're just building a protocol that works across all relevant blockchains, and that is supposed to transform how you guys as developers can leverage the power of ZK in a practical matter that makes it accessible for everyone. And to get a bit more into detail here, Boundless actually consists of many moving parts, but two main components. And one are the core services, which we call basically everything that handles the heavy lifting of ZK infrastructure. And extensions, those are the developer-facing tools to plug ZK directly into your projects. So basically think of the core services as the engine room of Boundless. So we try to design these services to be incredibly robust and efficient, but also in a way that you don't have to worry about the complexities of ZK implementations. So mostly this means there is a decentralized prover market. You just submit your proof to this, and then in permissionless system, any can run a prover and basically prove this. And of course, they cannot cheat because you can always verify that the proof is correct. Also, settlements, like how you can verify the proof on other chains, or how you can make sure that the payment of the prover works as it's expected. And one other important thing we called aggregation. So still like ZK verification costs a bit of gas and chain, but as I mentioned before, basically the complexity or the length of the execution does not matter. So what you can just do, you can just basically put multiple proofs. So as a prover in this network, for example, I can put the solution to many of those requests to those proofs in one bigger bundle. And then I just need one verification on chain, and the rest is basically ensured by composition. And of course, there's a bit of trade with latency and stuff, but this basically reduces the cost by 95%, to just give you an example. So those are the core services. How do I create a ZK proof, and how can I verify it? But as I mentioned before, there's actually more we as developers need. So we basically need some interaction between existing tools and existing stuff that we have and the ZK world. So there's, for example, Steel, which allows us to do like off-chain smart contract execution. ZK makes a lot of sense in the roll-up sense. So we have several tools that do this, like Kailua, or also data availability is another issue. So Blobstream 0 is an extension for that. And this all together is the Boundless protocol. And we basically build it so that this is all you're ever going to need if you want to interact with a ZK from your application. So yeah, and basically it plays all together, and depending on your application, your chain you're working on, you won't be needing all the parts, but maybe just some of them. Okay, so since we're here in a developer focused workshop, let's focus on those extensions first. And personally, especially interesting, I think, is Steel, because it really simplifies carrying over stuff you're used to doing in a Web3 Solidity world to the ZK world. So what does Steel actually do? And let me give you an example. That is actually from one of our partners, Eigenlayer. They, to basically secure their slashing, they have essentially a smart contract call that if you'd execute it, it would cost over 1 billion gas, because it has to do so many loads and stuff like that. And if you do the math, that would be over 40 blocks worth of execution of that, just this single contract call. Of course, that is not feasible from a space, but also a cost point. And now, basically, Steel super transparently, without changes to your existing Solidity code base, allows this to create a ZK proof of exactly this very complex execution. This, just give you some ballpark estimates here, is maybe $5 US. And then you have just one single proof, and that you need to verify on chain. If it's not aggregated, that is roughly 300,000 gas. It's one gross 16 verification. Just, I don't know, again, like maybe around $12 US, depending on your gas cost. And yeah, so this is one example. But of course, like, that's exactly why we called it Boundless. You could do even crazier things, like do more complex stuff, do longer executions, and it will boil down to the same one proof on chain, which is only 300,000 gas. So what does this mean? So it essentially means that you get unlimited compute, unlimited execution at a constant gas cost. And of course, there are additional costs that now come in. But as I showed you in this Eigenlayer example, the price of proving, like creating the actual ZK proof, is just a tiny, tiny fraction of what you'd have to pay if you do everything on chain, right? The $5 I mentioned earlier. And Also, the price of verifying this proof is only a tiny fraction of the price you'd pay on chain, namely only 300,000 gas instead of 1 billion or whatever. So what is Steel and how can it actually do that? So what it does is basically it tries to execute Solidity in some simplified version. It tries to execute Solidity code in the ZKVM so that you don't have to worry about rewriting the code and stuff like this. So let's maybe just look at an example. So this is a function from the Uniswap smart contract you may be familiar with. This is how a typical contract function in Solidity would look like. So it gets a bit of parameters, and then you want to call this functionality. In this case, it would be adding liquidity to your pool. But yeah, that's just one example. So how does this work? How does the EVM in Ethereum deal with that? So you prepare a transaction that tells basically, I want to call exactly this at liquidity function with the following parameters. That is ABI encoded. And that is the thing that you prepare, and then you submit it to the network, to Ethereum. And then what does Ethereum actually do with it? So it fetches the logic and the state. So the bytecode, the actual smart contract. So what is the Uniswap smart contract? What does it do? What's it supposed to do? And also the current state of the contract, namely maybe what variables, what maps currently have what value. That is basically the state that gets loaded into the Ethereum virtual machine execution. Then it performs the actual execution with respect to the given gas limit, and then it outputs the result. And typically in the Ethereum case, the outputs are state updates or events. And this needs to be verifiable because we're talking on a decentralized network, obviously. So as I mentioned before, other nodes in the network will need to rerun it to check that this is indeed correct, that you weren't cheating. And that makes smart contract execution is limited. So how would that same paradigm work with Steel or with ZK proofs? So first, let's start like very basic. What is an actual virtual machine? So if you go back to fundamentals of computer science, a virtual machine takes some kind of program and some data. And then it basically performs the steps it gets from the program on the given data, and then it manipulates stuff and it creates the output. And ZKVM is actually exactly the same thing. It has input, program, produces an output. But in addition to that, it also creates a proof that indeed, with respect to the given program, it had valid input. Essentially, it can be any input. You don't need to disclose the input. That is where the whole zero knowledge ZK name comes from. So it had any input, which led to the following output. And then the cryptography makes sure that this must be the case. No one can cheat here. Everything is sound, and you have all the guarantees you actually need. And we at RISC-0, I mentioned before, we have this general purpose zero knowledge virtual machine. And what does general purpose mean in this case? It is not a special purpose machine like the Ethereum virtual machine or something different. It can essentially take, let's say for simplicity, any Rust code you write, put it into the ZKVM, and it'll output a proof. And that's it. Anything you can do in a regular computer program, anything you can describe in Rust, you can do with the RISC-0 ZK VM. How would that look like a bit more in detail? So our ZKVM is RISC-V based, which is essentially an instruction set like the Intel x86 instruction set, and there are other ones. But it is a special instruction set that it hits very many sweet spots. It is rather simple, so the cryptography, the mathematics doesn't get too complicated, but still it is a standard instruction set. So essentially any compiler that can target this RISC-V architecture, which LLVM, for example, can create code for it. So no need to write any custom compilers or programming languages for that. So you can have the guest code essentially in any language that is supported by such a compiler. And then you create the binary, which is the computer program, and you run that in the ZKVM to get what is typically called a receipt, which is basically the proof together with the output. Okay, and Steel essentially aims so that you can input Solidity code into the ZKVM and get a proof. It's a tiny bit more complex than that, but that is the general idea, because that, as like a Web3 developer, is what you want. You want direct interaction with your Solidity code. So let's first get back how a transaction worked on a plain Ethereum. So you have this transaction, then you get the state and logic from the blockchain and you execute it. So how does this actually look in Steel? It is actually very similar. So this now you run it in some sense asynchronously, right? So the actual computation is no longer performed on-chain in a specific block. It is run off-chain. And then once you have the proof, you basically only submit this proof to the blockchain. And then, of course, the same mechanisms apply. So we don't want to build any new L1s or whatever. It is everything Ethereum compatible. So, of course, like the EVM of the Ethereum network will verify this proof and update its state accordingly. Okay. So far, this was the introduction on how it actually works in theory. And now let's look at how the code would actually look like if you want to use that, if you want to implement that in practice. So for this little tutorial here, we're using a very simple function, namely checking the balance of an ERC20 token. It's questionable whether what's the application for that would be, but that's just to serve as an example. Of course, you can do anything, but it needs to fit on slides and needs to be simple. So I think that is a good example to showcase something that is very Ethereum native. So this is how the check balance function would, for example, look like. It is important to note here that this is a so-called view function, which means that it does not modify the on-chain state. And that is actually important. While it is possible to change the state coming from some Steel execution, this gets a bit weird because, as I've mentioned before, it is asynchronous. It is no longer atomic. So the proof creation takes a few blocks, right? So you make sure that the state is still consistent. So for simplicity, and actually in almost all of the use cases, it's sufficient to look at view functions, and we don't have to worry about the state changes that happen. So now we want to use this basically as input to our ZKVM. And while essentially you could use a whole variety of languages, we usually recommend Rust for various reasons. We have the best support for Rust, but also the tooling, especially for Ethereum, for blockchains, is usually very great with Rust. And this is one example. For example, in Rust, you have the awesome Alloy library. And this Alloy library comes with a so-called Sol macro, which essentially translates for you any Solidity type, any Solidity function into the corresponding Rust types. So you just paste exactly the function like we saw from the Solidity side. You paste it in here, and then Alloy or the Sol macro will make sure that this gets translated into Rust, and you don't have to worry about anything. Okay, so that given, how would the actual guest code, so the code that runs inside the ZKVM look? And that is very simple. So you have the balance of type now, which basically declares this function. Then you need to actually create this or make it an actual call. So you need to fill in all the parameters. So in this case, you need to fill in the actual account you want to query the balance of. So this makes it the call. This would be exactly what you submit in a transaction in a traditional Ethereum. And then you basically need to make sure like this gets called. You need to specify on what contract address, so contract tiers and address, with a given environment. And the environment essentially holds the state input of the blockchain. And this is actually kind of important. So we're going to talk a bit about this more in details. Then you get the result back. Again, Alloy makes sure this the types or whatever are all good. So you get back the balance. You compare it. In this case, you just make sure it's at least one token, right? So that is basically your computation. In this case, the very trivial one, but you can do much more complicated stuff. And then you have to prepare the journal. The journal is basically what we call the output, the verified output. This is once the commitment. So basically the input was correct. We talk about this. This is actually very important. So we talk about this a bit more in detail later. And also, let's say the contract address you called it on, you ABI encode it so that it's nice and handy on Solidity. And again, the Rust ecosystem has awesome tools for that. And you call commit slice, which is basically the RISC-0 way of saying this is supposed to be part of the output. And that's it. That's now the whole guest you need to basically call this this balance of function, check that the value is at least 1, and prepare everything. So, but now the key issue is obviously what I kind of gets hidden or abstracted away here is this environment, right? Can we actually trust that Steel executed our view call on the correct chain, on the correct with the correct data? Maybe the data was modified and I have much more balance than I was supposed to. So how can I make sure that is correct? And actually, the kind of the magic is it's not aliens. Steel does this exactly for you, and not only Steel. We are heavily relying on Revim, which is an Ethereum virtual machine implementation in Rust. So how does this work? So in general, you have this paradigm, which you might be familiar with general virtual machines. You have the guest program. That is the guest that runs inside our ZKVM, and you have host program around it. The guest itself is kind of stateless, like it doesn't have internet connection, it doesn't have DB, right? It must, then the state always resets. It only gets a certain input, which is prepared to by the host, right? And we can use this paradigm now to make sure that the data we use is correct. So in that case, the host would actually do the heavy lifting. You'd also have to tell the host which contract you're calling, and then it would basically connect to an archive node. It would ask that node, what is the storage, what is the state at that point, and also please create inclusion proof, a Merkle inclusion proof for that. And the Ethereum RPC API offers the ETH get proof call for exactly that. And all this then gets wrapped and condensed into the EVM environment. And it's important here, you obviously don't load the whole Ethereum state. That would be gigabytes or even terabytes into your program. That would be much too slow and much too big, right? But you're only interested in a tiny portion of the state. So that's what I mean. You basically pack everything, only the stuff that you need, into the environment. And then what the guest program, what Steel actually does first, is verifies that all these input is correct, that the miracle proofs are correct. Then it calls the actual view call using the REVM virtual machine verifiably in the guest. And then you get the receipt back that I showed you. So that means you also need a bit of host code before this. Essentially, this more or less, this exactly mirrors the code you have inside the guest, because as I mentioned, you also need to tell the host which contract you want to query, which function you call, right? And you also need to specify an RPC provider. So let that be your own full node, or I don't know, Alchemy or another RPC provider. And then it fetches, the host fetches the data from that node and prepares the input in the last line. Okay, and then how would the entire guest program look? So you'd first read that input, that is the whole packed thing, the witness with the proof data, maybe also the contract address, naming like which ERC20 token you're actually querying, let it be USDT or whatever, and maybe also the account that you're want to get the balance of, right? And then you do the stuff we saw already and commit to it. And this is literally everything that you need inside the ZK VM. So it's very simple, and all the complexity is taken away by Steel. Okay, so now you have this, and now you of course want to do something with it on chain, right? That is the whole point, right? You need to basically carry this off-chain proof back. And there are basically those three things you have to do. You have to validate the journal data, you have to validate the Steel commitment and verify the proof. And only if all three of them are correct, then you actually do the thing. So yeah, let's to better understand this, let's maybe look at this like with an actual concrete example. So let's say you have this example smart contract. As I said, again, it is just an example. So what it does is basically it increments and counter anytime someone submits an address which has a certain ERC20 balance of at least one token, right? And this is how the code would look like if you want to write pure Solidity. Very straightforward. You query the balance, check whether it's at least one or more than one or whatever, and then you increment the counter. That's it. So how would that part now look if I say my actual check is performed off-chain with ZK? You need to verify those three things I mentioned before. So first, you basically need to decode your journal. If you remember in the guest code, it was actually ABI encoded, so I can just ABI decode it here to get my journal back. The journal consists of two things: the contract, namely which contract I'm actually calling. And you see here, it is very important that you check this here. And this is a common mistake that happens in ZK. So to reiterate on that, what a ZK program actually proves is that there is any input that led to the corresponding output. So it doesn't give you any guarantees that the input you wanted was also used. So you need to make sure that this is indeed correct and that the correct input was used. And in this case, this means here, even though I have a proof, right, that there is a certain balance of at least one there, maybe the creator of this proof swapped the token contract and just proved that the balance is of a different coin than ERC, than USDT or whatever, right? So you need to check that this is actually correct, that the guest actually used the token, the ERC20 contract you're expecting. So this happens here, and there might be other things depending on your use case to check that. And then you need to check what we call the commitment. We'll go a bit more into detail about what the commitment actually does. So I leave this out for now. And then the actual thing is the execution proof. That is what you think, like the ZK proof. And we have verifiers for that you can just call. We have them deployed on all major mainnet and devnet chains, so that shouldn't be an issue. Also, obviously, you can deploy your own verifier if you don't trust our deployments there. And this is how it would look like. And also to validate the Steel commitment, we've provided some libraries to make life easier. So just to summarize this, Steel can offload massive execution verifiably on chain. Obviously, for this example, just taking the balance, it does not really make sense yet. But as I mentioned, you can do arbitrary complex stuff, doing billions of gas, or I don't know, 10,000s of S loads or whatever, and it would work exactly the same way. So now let's talk about Steel commitments. And actually you can, I don't know, give a brief overview here. If you want more information, feel free to look at our GitHub. We have like documentation there. We have a lot of examples there to showcase this. So again, the line here marked validate commitment. This is so far we've seen this as a black box. And I want to talk more about how this actually works, what it means, and why is it necessary? Why isn't it just the ZK proof? So this was how our journal looked. It is the commitment and the token address. Now, I already explained the reason to you why you want to have the token address in the output. And that is also the commitment. So Steel uses the blockchain state at a specific block, like obviously, right? You want to call a function, and if you'd call it in a block on chain, this would be exactly that, right? It would take the state of the current block, it would execute it and produce the result. So we want to replicate this off chain. So Steel needs to use the same state as a specific block. You can obviously specify the block, which block you exactly mean. And then it basically, thanks to the Merkle inclusion proofs, it reduces all the state data, everything it uses, the contract code, the states, everything. It reduces to essentially the block hash of that block, right? And you put then that block hash in the output, and then again, you need to check that the block hash is correct. Otherwise, I could have executed my Steel on Sepolia instead of mainnet, and obviously the result would be vastly different, right? So this is essentially what the Steel commitment is, and this needs to be validated. But the beauty here is, as long as you can somehow validate a block hash, you can verify the Steel state and you can verify a Steel commitment. So you can trivially verify the block hash, but maybe you want to store it in a smart contract, you can do it. Maybe it gets passed to you via messaging, like from L2 to L1. You can do it like that. You can create an inclusion proof of the block hash, maybe in the consensus beacon block, and then use a light client state or whatever. You can do that. So there are a lot of possibilities as long as you have this block hash somehow available. And as I mentioned before, we have some hard-coded or some implemented validators for you readily available. The most simple one is using the block hash opcode. There's an opcode in the EVM that just, you give it a block number, and it basically returns the block hash of that number. So you can obviously use that to check that the block hash is indeed correct. This is, if I remember correctly, around 20 gas or so. So it's super, super cheap. But the drawback is it only stores the latest 256 blocks. So that is roughly 50 minutes. So to create your proof, to get it included in a block and on chain, it must not be longer than 50 minutes. But if you have this, then this is the most simple, the cheapest, the most efficient version. As an alternative, like with Denkun, Ethereum introduced the beacon block route. So basically there is a pre-compile or a pre-deployed contract on Ethereum that stores the beacon block routes of the past 24 hours. And you can use that to verify the Steel commitment. And this gives you a time window of 24 hours. But there's also something like we call history commitment, and that is something like you can see this like recursive verification. So you essentially verify the Steel commitment inside Steel and again and again. And so with that, you can basically, with each iteration, you can always jump 24 hours in the past. So this essentially gives you unlimited time windows if even the 24 hours is not enough with you. And the drawback is it makes the gas program a bit more complex, like cost-wise, if you want to create the proof, but it's not so much. Okay, so that basically sums it up. So to basically summarize everything, so Steel offers ZK smart contract execution for Solidity developers. You don't need to rewrite your Solidity stuff. You can call native Solidity view call functions and don't have to worry about anything. It does this by essentially running a minimal EVM in the guest environment. We use Revim for this, and it only uses the data that is actually needed. And for that, the host needs to pre-compute data, and we do this like in a verifiably way so that you get the same security requirements. And then what you need to do on-chain is you need to do the commitment check. There are a lot of possibilities how to do that. We also have like examples at our GitHub, and you can see how you meet, I don't know, maybe cross-chain commitment verification, so that you can verify an OP Steel proof, Steel commitment on Ethereum L1. And you, of course, have to do the actual ZK proof verification, which is one Groth 16 proof. Yeah, so this is the cost, the fixed cost you have to pay, but this is literally the only cost you have to pay. It no longer matters how complex the view call is, and you can call multiple functions. You can do even event processing, which is something that you natively cannot do in a smart contract. You can still do that in Steel, and everything boils down to this constant cost in the end, and you can use the result on chain like you'd used to. Okay, so that was it. I hope that gave you some kind of practical introduction in how you'd use Steel to actually develop some ZK programs, and then some overview how the Boundless protocol itself can help you get this ZK work done. So that's all the slides I have. So I don't know, are there any questions or remarks?
Yeah. I have a question. Both host and guest program run if I run the Steel code, the host program and the guest program run in my local PC.
Yes, that's actually a very good question. So currently, that is the default way. So you would run the host program on your local machine. This is why I basically, in this example, I showed you how you can specify an RPC provider, right? Or your full node or whatever. So then your local machine would basically prepare the input for you and then the guest. The guest itself is essentially you don't need to run this on your local machine. You can, we have our ZKVM works on your local machine and is also reasonably fast. But especially if we're talking about like huge contract calls, this would take a very long time. So here's exactly where you would submit this to the Boundless network, to the Boundless proving network. So basically what the host program gives you, it gives you the program binary, right? Plus the input, which is all this condensed stuff. And you would, there's also a client for this for the Boundless network. You would basically then use the Boundless client to submit this to the Boundless network. And then any prover can approve this for you. Because for example, if you have a GPU data center, that is the most efficient way to tackle like huge proofs, talking about billions or even trillions of gas or whatever. So some data center provider could pick up this proof for you if it's complex. You'd pay them over this marketplace and you get the proof back. And you don't need to worry about anything. You don't need to re-execute the guest because you have the proof and know that this was run correctly. And then you can do all the stuff that you mentioned. But with the current stuff, it is still expected that you run the host on your local machine. We have like plans that even simplify that you can basically tell the Boundless network, I'm interested in a view call of that contract with that input, right? And then the prover basically runs the host program for you. It fetches the data from RPC provider, all this stuff. But this is currently not there. So currently you'd run it on your host machine, but that's not an issue. It doesn't take too long as long as you have access to a fast Ethereum full node.
Okay. If run my computer Apple M4 10 view cores, like just like a balance of how much time need generation for the proof.
If it's just a balance of, that is very fast. I don't have the correct, but it's order of minutes, like 3 minutes would be my guess. And then you also have to make a Groth16 proof out of it, which so that Ethereum understands it, which is another minute or so. So that we are talking about orders of minutes here. But of course, like the example I showed you, the 1 billion use case from EigenLayer, that would take hours or maybe days on a single machine. And that is exactly why we solve those huge proofs in a data center, which has a lot of GPUs.
Okay. Another question I want to know, the Steel only support the view core know the status on the chain?
Very good question. So yes and no. So Steel, you can essentially call any function in Steel. It doesn't matter whether it's view call or not. It is just that the guest is essentially stateless, right? So any state modifications that this call made are essentially lost. You still get the result back. So this function might change the state and return a result, right? But the actual state modification, of course, are lost. And then it is up to you what you do with it. I could, for example, see a use case where you're just interested in the, I don't know, in the slippage of a certain token swap, for example. Then maybe you do the swap, which is a stateful call. but you're not actually interested in doing the actual swap, but you just want to have some guarantee that the slippage would be so and so, right? In that case, you can use Steel as it is, and you can create the proof. If you, of course, want to replicate those state changes on the guest, on the chain, it would be more complicated. If it's just a few state changes, this is still possible. You essentially write the slots that change into your journal, right? And then the verifier contract on chain would not only check the proof, but then afterwards also basically iterate through all the slots you changed and actually perform the actual changes. So we also have an example for that, but it gets very ugly. And again, you get a lot of costs, right? If you have to set a lot of states. So in my experience, for most use cases, this is not really necessary. The statelessness is already very, very powerful.
Okay, I understand you. If I write some on-chain game, this game also can run on off-chain. It's possible. Or both
Yes.
on-chain game and the off-chain game.
Yes, you
same
can.
Code.
It would it would be this exactly. It would be like you have the function written in Solidity, and then it's your option whether you call it directly on-chain this Solidity code, or whether you use Steel to use exactly the same code off-chain. Yeah, exactly.
OK， 其他人有没有什么问题？大家可以那个直接留言也可以。Anyone question? No more question. OK. Thank you, Welz, for your insightful and engagement presentation.
Yeah, I hope it was interesting. And again, check out our GitHub. We have docs, we have examples for that. If you want to really develop, play with it, do that. Yeah.
Thank you again.
Thank you.
就说拜拜。
拜拜。